Thank you for the introduction. So it's Friday and it's last presentation. Everybody looks unhappy. I think it's wrong. Now I will present a new transducer technology based on a granular chain, and we want to generate wideband impulses. It's the motivation of our work. Why you want to generate a short duration and wideband impulse? Okay. So the first benefit for imaging is pretty obvious. You improve the resolution, so you can do better imaging. And the second benefit, it's a bit more subtle. If you create a wideband ultrasonic impulse, it will have a rich harmonic content. So you can increase the potential for harmonic imaging and also the multipulse imaging techniques. For therapy, you can create a compact and dense high energy region and reduce the possibility of hotspots. In histotripsy, if you can generate a short duration negative monopolar pulse, it will inhibit shock scattering. And for HIFU applications, you will have a precise control of the focal region, which will also minimize the potential collateral damage to the healthy tissue. Does this sound okay? When I say granular chain, I mean a one-dimensional chain of steel spheres. They are compressed with a precompression force of F0 and excited from one side with a force of Fin. For this case, we want to use a narrowband excitation, which Fin, like a sinusoidal wave. And on the other side, we expect to get an impulse, a wideband signal. So in this chain, there are usually three different types of waves are observed. For the first case, if you compress the chain too hard, if the F0 is really higher than the Fin, then you will observe a linear dispersal wave, which means this chain is going to act as a solid material. For the second case, if you increase the input force, then you will start to observe nonlinear effects. This is due to the Hertz in contact. This sphere is going to lose contact, and it will introduce nonlinearities. And if you further increase the input force, then you will start observing strongly nonlinear effects. When I say strongly nonlinear, I mean the relationship between the force and the displacement. Now they are not going to be scaled, linearly anymore, but with a power law of 3/2. So it creates a strongly nonlinear wave. And when the spheres are not contacting with each other, the energy transfer to the next sphere is effectively zero. We also have a model which shows the behavior in a chain. It's published recently in Europhysics letters. If you're interested with our model, please have a look at the paper. So this is the device we are coming up with. I'm using a 40 kilohertz ultrasonic transducer, and there is a horn at the end. Why we need the horn is because I want to create lots of input force. So I need some mechanical amplification. This horn is going to give me lots of mechanical amplification. So I will create higher input forces. And at this end of the horn, I will put this 3D printed mold, which is a bigger version here, zoomed in. And these spheres are going to sit inside this mold, which are 1 millimeter diameter. So how to put everything together? I put them in a cage assembly. This is a transducer fitted in a cage assembly. And this is that small granular chain where the spheres are fitted in another assembly, and I can put them together. There are holes in this one, and this rod fits into it. So I can slide it back, and there are small screws that I can screw and fix the pre-compression force to this system. And also on this side of the chain, which you can't see clearly, but there's a coupling lens. It sits here, so spheres are not in contact with water. So this is the final instrument. It looks like this, and it has a fixed pre-compression force of 1.2 newtons, which means it's a portable compact device. You can rotate it, turn it, carry it, and it will give you the same measurement, same response. First, I characterize the input to the chain, which is the output of the ultrasonic horn, because I want to make sure that I'm not getting too much harmonics, because I want to use a narrowband signal and generate an impulse. So for me, my input to the chain should be as clean as possible. So this is the frequency response of the chain. I measured the velocity and displacement output of the chain, and the harmonics are less than 60 dB. So I'm going to assume that the input to the chain is a clean signal. And this behavior of I'm not putting a signal like this. This comes from the amplification effect of the horn, and the rest is because it's a high Q device, it gives you lots of ringing. So Even if I want to put a narrowband rectangular signal, this is what we're going to get usually end of the horn. Another issue was I'm using a 40 kilohertz horn. Yeah, it's really good. It gives lots of force. But 40 kilohertz is too low for any biomedical ultrasound application. So I measured the impedance of this horn. There are other resonance peaks as well. So I focused on the other ones and did measure the displacement and velocity too. And these are the results what I get. I showed you an equation before. The force is related with the displacement. So what I need is a high displacement. But this is a trade-off you always get. If you increase the frequency, or even choose another transducer, you will start getting lower displacement values. So this is a trade-off which I cannot do anything about it. But I also measure the velocity, so it is actually a fair comparison for this case. Because if you look at the velocity values, you see at this frequency, 265 kilohertz, I get similar velocity values compared to the 40, which means actually it's an efficient resonance peak. Unlike this one, for example, it's nearly the half. So put everything in water, let's make some measurements. This is the experimental setup. It looked a bit complicated, so I put an illustration here. This is the blue thing here, which is the active element. I put a narrowband signal. This horn is this part, which amplifies the effect. And there are spheres, these are exaggerated, these are millimeter spheres inside here, you can't see now. These spheres are coupled to water with a coupling lens, so they are not in contact with water. And on the other side, I have a membrane hydrophone to measure the pressure. Okay, first thing, I plotted the spectra because I want to characterize the nonlinearity of system. It's not easy to characterize the nonlinearity in the time domain, but if you go to the frequency domain, you can analyze the harmonics and comment on the nonlinearity generated by the system. So I'm looking at the 90 kilohertz one here, the red one. So I can generate up to the 6th harmonic above the noise level. It's quite nice, it's a nonlinear system, but it's nowhere close to a megahertz range. It's not going to be helpful for any biomedical application. Okay, second case is 150 kilohertz. It generates 2nd harmonic and the 3rd harmonic actually doesn't have too much energy. We know why this is happening because I measured the velocity and this resonance peak is not an efficient resonance peak for our input transducer. But at 265 kilohertz, I get quite a lot of velocity displacement output, velocity output, and it generates lots of harmonics and it reaches nearly the megahertz range. Okay, now we can look at the time domain signal and comment on it. Time domain signal looks horrible actually on this case because input of the signal is this. This is the input to our chain, and the envelope of the pressure wave is distorted. Why? Two reasons. Because the first reason is noise, obviously, and the second reason is some repeatability issues we spotted later. There's a friction inside this chain. It's touching to an acrylic mold, and when there's friction inside the chain, this sphere doesn't go back to their equilibrium position. If they're always back to the same position, we expect what's going to happen. But if there's a lot of friction, I mean static friction, it's going to stop the balls from moving. Then you will have repeatability issues, and I think it's why the shape of the envelope is changing. However, if we focus on, for example, this region, the peak region, we see shocked waveforms. It's similar to HIFU signals you see in water, high positive levels and low negative levels. It's not a shock wave, it's just a shocked waveform, and it's generated around 10 kilopascal for this case, which means the nonlinearity is coming through the chain, not generated in water. We can safely say that. And I did repeat the measurements because I said there are some repeatability issues. I did make another mold and repeat it again at different input velocities. The theory says that increase the input force, you will get more harmonics, more nonlinearities. And actually we are getting more nonlinearities for the high voltage case. And we can cover the range of 265 to roughly 1300, which is a megahertz bandwidth impulse. Actually useful for biomedical applications. Okay, let's compare this with theory. I got this nonlinear effects, but is it true? Is it what we expected, really? If you look at these equations again, okay, it's not linear. We can easily eliminate that option. Second option is, are they in a comparable level? I measured the input force. It's around twice the precompression force. However, I can't safely say it's in a strong nonlinear region. I think it's still somewhere in between. We are not getting impulses as wideband as we are expecting. So I'm going to be critical and give some pessimistic conclusions about my work. First limitation is the transducer. As I told you, the frequency should be high, but for high frequencies you get low displacement values. So there's always a trade-off between choosing the right input transducer. The second pessimistic conclusions are the repeatability issues. We did use a 3D printer, and it has an accuracy of 15 micrometers. It sounded really nice when I first tried it, but if you have 1 millimeter chains, it will give you an error of 1.5. And it's going to increase the static friction between the holder and the spheres. So it's going to reduce the repeatability. Another repeatability issue is related to the pre-compression force. I want to reduce the pre-compression force as much as possible to increase the nonlinearities. But if you increase the pre-compression force, your device is not portable anymore. When you start moving it, it loses contact and you don't see the nonlinear effects you're expecting. And the last issue, I think, is the biggest issue here, the output power. We are limited in the kilopascals range. So it's 10 to 20 kilopascals, the output pressure, but we need megapascals to use it for therapeutic applications. So this is unpublished work yet. I just finished measurements literally a few weeks ago. And I did improve actually the transducer and the setup. So what we are looking at is the F0 is now a lot higher than the F8. So we are in the strong nonlinear regime. So the right-hand side is the simulations. We expect a behavior like this. Impulses with lower negative velocities and higher positive velocities. And it generates lots of harmonics, up to the 10th harmonic. And if I want to compare the simulation results to measurements, so I need to flip this one upside down, because plus velocity gives me negative pressure. So if you want to compare a fair comparison with like this, we are seeing a very comparable, nearly the same response with the measurement and the theory, and it generates lots of higher order harmonics. And now the pressure levels are around 6 to 70 kilopascals, which means we are getting there, and also it's a single chain. If I put 10s of them, 20 of them together, which is really easy to manufacture, I can easily get an order of magnitude higher pressure level than this. And also I want to thank my collaborators from the University of Warwick, University College London and University of Leeds, also EPSRC for funding this work. Thank you very much.